Hello everybody, welcome back. It's another quantum computing video. Today we're going to work with Single-qubit on Jupyter Notebook. We're going to see a lot of cool stuff, how to draw a circuit, a single qubit, and where is that qubit on the sphere, block sphere, great visualization. We're going to talk about self-inverted gates and also gate inverse pairs, work with Quirk and also with the IBM Learning platform. So watch the video until the end and let's get started. We need to install all these things. We need to run and create our quantum circuit, and we're going to start with the Hadamard gate. The symbol is H. The H gate creates a superposition state. It transforms the basic states K0 and 1 into an equal superposition of both states. It rotates around the axis pointing halfway between X and Z. Think of a coin spinning in the air, not get landing on heads or tails. The Hadamard gate puts the qubit in this spinning state where it is both 0 and 1 at the same time. Actually, it's not both 0 and 1. It has equal probability to get a 0 and 1. So if we need to draw, this is how we can do that. And we need this code to get our matrix. This is the unitary matrix. We need it for the math. When you work with quantum computing, you need math, you need physics, and also trigonometry because you need to find the angle, the theta and phi angle on the block sphere. This is the state vector. It says that we have 50% probability to be on state 0 and 50% on state 1. Okay, the 0 goes up, 1 goes down, and this is the block sphere. We applied Hadamard gate, so from here we moved it to the equator of the block sphere. This is the visualization. Unfortunately, it's going to be removed, but let's play, okay, in a loop. As you can see, from 0 it goes to X. And if we want to see the histogram, the plot histogram, we can see that we have 50% to be 0 and 50% to be 1. So let's move to Quirk. And as you can see, everything is here off. They're moving the Hadamard gate, and you can see that we have 50% to be 0 and 1. Now let's see that again on the IBM platform. We have Hadamard gate, 50%, 50%, and the same on the block sphere. Okay, now let's create a Pauli X gate. So a Pauli X gate is a NOT gate, and the symbol is either X or plus. The X gate is a single qubit gate that performs a bit flip operation. It transforms the state ket 0 to ket 1 and vice versa. Mathematically, it's represented by the pole matrix. We're going to see it later. And the rotation is around the x-axis. Imagine a light switch that can be either on or off. The X gate flips the switch, turning it on if it was off and vice versa. So we need to run again our circuit to create it. Let's draw it. As you can see, it's X, the symbol. And let's see the unitary matrix. This is 1. Now let's get the state vector, 0, 1. We need also to run the block sphere. So it's moving to 1. Why? Because every time we start, the qubit is on position 0, gets 0. So with X gate, it comes down. Let's run the visualization. Wait a little bit. It takes some time. And let's run it. As you can see, applying X gate from ket 0, it goes to ket 1. And also, let's see over here. As you can see, it is 100% that it's going to be 1. Let's see that again here on Quirk. This is the Pauli X gate. Let's apply that. As you can see, it comes from North Pole to South Pole, and you can see that the theta angle is 180 degrees. It has 100% probability to be 1. Let's move to IBM Learning platform, and let's take the X gate. As you can see from here, we have 0 because the sphere is here. So the NOT gate, as we expected, 100% to be 1, and it moved over here. Okay, next is the Pauli Y gate. So we are going to apply that. The Pauli Y gate, the symbol is Y. We're going to draw it later. The Y gate is another single qubit gate that rotates the qubit state by 180 degrees around the Y axis in the block sphere representation, and it modifies the shape of a qubit. Think of a spinning top, and the Y gate rotates the top 90 degrees on each side. So let's run and create our quantum circuit. Let's draw that. Perfect. Let's see the unitary matrix, and let's get the state vector. Perfect. And now the qubit, and let's see the visualization. So from here, as you can see, it moves 100 degrees, and also the plot histogram again 1. So now let's go to Quirk, apply the Y gate. As you can see, if we remove that, sorry, Y gate, it goes to 1 with 9 degrees over here, 100%. And let's go to IBM. Let's remove the NOT gate. This is it. Next is the Pauli Z gate. So let me comment this and apply the Pauli Z gate. The symbol is Z. The Z gate introduces a phase shift of p radians to the Ket1 while leaving the Ket0 state unchanged. Mathematically, we're going to see the unitary matrix, how it is represented. And imagine a coin spinning in the air. The Z gate flips the coin's face, making it spin in the opposite direction without changing its hands or tail state. So Ket0 remains Ket0, but Ket1 becomes negative Ket1. So now let's create our circuit, apply the Z, let's draw it. We need to get the unitary matrix. This -1 is what is doing all the job, the phase flip. And let's get the state vector, the block, and the transition. I don't think we're going to do anything here with the visualization. Yep, we cannot see something. So let's go up again. And now we're going to create also a Hadamard gate. We're going to apply Hadamard gate and then the Z gate. Let's create again our circuit. Let's draw that. Okay. Of course, the unitary matrix change, also the state vector. And now we're going to see something different on the block sphere. Why? Because first we apply the Hadamard gate, so from K0 equal to X to equator, and then we hit the Z gate. Now the visualization is going to show us something. Okay, and let's run it. We have the Hadamard gate and then the Z gate. Perfect. Let's go now to Quirk. So over here If we move the Z gate, nothing changes. So let's apply first a Hadamard gate and then a Z gate. So we have 50%, but over here you can see that we have the phi until 180, which means that it rotated uh, to the other side of the circle on the x-axis, and theta, it rotated 90 degrees from top to the x-axis. Let's go back to explain what I'm talking about. So the phi angle goes around the sphere, okay, the equator. The theta angle is this over here from z, how far away it's moving. This is why we need trigonometry. Find these two angles. This one, phi, and theta. Let's move to IBM. So again, if we apply just a Z gate, nothing happens. So let's put first to a superposition, Hadamard gate, and then a Z gate. As you can see, we have probabilities, and over here we have the K0, K1, but as you can see, it is red because we have minus. This is P 180 degrees. Next is the S gate and T gate, but first let me comment this too. Okay, so the S and T quantum gates are also called the phase gate. The S gate is called the phase gate, and the T gate also called the P8 gate, and are both quantum operations that rotate a qubit state around the z-axis of the Bloch sphere, but by different amounts. So the S gate rotates by 90 degrees, and the T gate rotates by 45 degrees. Imagine you have a globe representing the Bloch sphere, and you are looking straight down at the North Pole. Now imagine there is an arrow pointing from the center to the surface. The S gate is like rotating that arrow by 90 degrees by a quarter turn. The D gate is like rotating the arrow by an eighth or 45 degrees. The T gate is particularly special because it's one of the fundamental gates needed for universal quantum computations. While the S gate can be constructed by applying the T gate twice, the T gate itself can be broken down into simple operations. So I'm going to apply first just an S gate to see the unitary matrix and the state vector. And then we need to apply also the Hadamard gate. So this is the unitary matrix. And now let's get the state vector. Perfect. We cannot see anything, so I'm going to run the rest. Let's come over here, and first let's apply also a Hadamard gate to put everything, to put our qubit to the superposition. So we can see that we have the Hadamard and then the S gate. Of course, the unitary matrix is going to change, also the state vector. But now we can see something different over here. Okay, let's run the visualization and visualize the transition. And let's come over here and play Hadamard gate and then S gate. So the Hadamard gate comes from gate 0 to X to plus and then rotates 90 degrees and comes here to Y. So let's come to Quirk and we can take the S gate. As you can see, nothing is changing. Over here, just go over above the S gate. You can see that Phase 1 is changing by 90 degrees and it rotates around Z. So now let's apply a Hadamard gate before this gate. As you can see, it's 50%. We have rotated with 90 degrees, both on phi angle and theta angle. And it stays the same. As you can see, it stays the same. And the phase of one, it changed by 90 degrees. And here it says it changed. And let's see also on the IBM platform. Again, let's apply first the S gate. Nothing's done. But then let's apply the Hadamard gate. Okay, 50%. And over here you can see we moved 90 degrees, and over here you can see the color. In the previous example it was red because it went to P, which is minus. Now we have over here now the gate 1. Now let's see the T gate. Let me comment. And first, let's apply just the T gate. Let's create our quantum circuit and draw it. Perfect. Let's see the unitary matrix, our state vector, and we cannot see anything and changes on the block sphere. So let's come up again and also apply Hadamard gate and then our T gate. This is the unitary matrix and our state vector. And now we can see the difference. As you remember previously, it moved from gate 0 to X and then 90 degrees, but T gate it is moving 45 degrees. We can also see the transition over here. And let's apply that. Hadamard gate and then T gate. Perfect. So let's move to Quirk. Let's apply first a T gate. As you can see, nothing is changing. T gate over here, you can see that gate 0 is not affected, but the phase of gate 1 is changing by 45 degrees and it rotates around Z axis 45 degrees. So in order to see something, some changes, let's put our qubit on a superposition. That's why we're applying the Hadamard gate. And as you can see, it has moved over here 45 degrees on phi. And theta is moved 90 degrees, 9 degrees from Z, okay, it moved from top to the equator and then 45 degrees over here. This angle, this is theta and this is phi. Now let's go to IBM. We have T, nothing is happening. Let's apply Hadamard gate first. And as you can see, we have probability is 50%. Then over here, we can see that the angle has changed by a quarter, 45 degrees. Now we are going to talk about the self-invert gate. So previously we saw 6 gates, Hadamard, the Pauli X, Y, Z, the S and T gates. Now we're going to talk about the self-inverse gates, which are Hadamard and the Pauli X, Y, and Z. Let me explain self-inverse quantum gates in simple terms. Let's understand what self-inverse means. If you apply the same gate twice, you get back to where you started. It's like doing something and then undoing it. Think of it like toggling a light switch. Flip it once to turn it on, flip it again to turn it off. You're back to the original state. So all these gates, if we apply them twice, we are going to get the original state. Okay, so why are they self-inverse? It's because these operations are designed to be perfectly reversible and symmetric. In mathematical terms, they are their own inverse operation. It's like having a perfect undo button built into the operation itself. Just like how going one step forward and then one step backward brings you to your starting point. These quantum gates perform complete reversible transformation that, when applied twice return the qubit to its original state. So now let's create a new quantum circuit, and we're going to apply two Hadamard gates. Let's draw that. This is the unitary matrix vector. Of course, we cannot see any change over here, and that's why we're going to create the transition to visualize that. Okay, so let's play that. First Hadamard gate and then second Hadamard gate. As you can see, we started from K0, we turn to K0, and of course the histogram. So let's go to Quirk. Over here, if we apply Hadamard gate, we can see that we have 50% for both states. And then if we apply the second one, again to the original state, let's remove it and go to IBM. So one Hadamard gate, we have 50% to be on gate 0 or gate 1. We can see that also on the sphere. And then second one, and back to the original state. Now let's apply twice the Pauli X gate or not gate. Again, let's create our circuit. Let's draw that, our matrix, the sphere, and let's see the transition. It's ready. As you can see, it moves and then returns to the original state. Again, we can see that on Quirk. As you can see, it moved from 0 to 1. Now it's 0, it becomes 1, and then back to 0. Let's see that also on the IBM platform. From 0, 100% to become 1, and then back to the original state. Let's continue, and now let's see the Y gate, but in order to see some changes, we need also to apply a Hadamard gate. That's why I'm going to comment everything over here and create a quantum circuit. Let's draw matrix, the plot. As you can see, it comes to the equator, and let's wait for the transition. Is ready. Let's play that. The Hadamard gate, Y, and then back to the original state. Let's come over here. So Hadamard gate, and then the Pauli Y gate. So as you can see, everything is the same over here. and then we apply. It transforms 0 and 1, as you can see over here, and then back to the original state. Again, Hadamard gate, then y, and then again y, and back to the original state. Let's check our Z gate. Again, we need to apply first a Hadamard gate if we want to see some changes on the transition. Let's wait to create a visualization. It is ready. So let's play Hadamard gate, and then Z gate, and then Z gate. Again to the original state. Over here, Hadamard gate, and then Z gate. Remember that it changes the phase of 180 degrees. So let's apply again the second one and back to the original state. Also, let's see it on the IBM platform, the Hadamard gate, and then the Z gate to change over here the phase from 0 to P, and then another one and comes back to 0. Now we are going to talk about the gate inverse pairs. We've seen that S gate moves by 90 degrees and 45 degrees with T gate. So why can we have the self-inverse pairs also for S and T? It comes down to the rotation angles. A self-inverse gate typically involve 100-degree or P rotation or similar transformations that, when applied twice, return to the starting point. The S gate rotates by 90 degrees and the T rotates by 45. So for a Hadamard, not Hadamard, sorry, for X, Y, and Z gates, doing once we get 180 degrees, doing twice it's a 360 back to the start. So if we have an X and X gate, one next to the other, we get back the I gate, which is the identity. For S gate, if we do it once, we get 90 degrees, twice 100, three times 270, and then we need to do four times to go to 360, back to the start. We can understand that for T gate, we need to do that 8 times to get back to the start. That's why we need separate dagger inverse operations for S and T gates to undo their rotations in one step rather than having to apply the gate multiple times to get back to the starting point. So over here, let's create our quantum circuit. Let's draw that. Let's see the block sphere, and we can have the transition visualization. Perfect. And let's play that. Hadamard gate, and then 90 degrees, and then the dagger takes it back. And the histogram, but we don't need that for now. Now let's move to Quirk. Let's apply Hadamard gate S gate. As you can see, it moved. Okay. Do you remember that it changed the phases of 1 by 9 degrees? And now let's apply the S dagger and it comes back. Let's come to the IBM platform, Hadamard gate, S gate. You can see we move the angle 90 degrees. And now we get the S dagger and it comes back to 0. Now let's come over here to the T and T dagger gates. Let's create a quantum circuit, apply the gates, draw. Let's see what's going on the block sphere and wait for the transition. We will see first the Hadamard gate from gate 0, come here to X, to the equator, moving 45 degrees and then returning back. Hadamard gate, T gate, and then T dagger. Let's move to Quirk. We need the Hadamard gate, T gate is going to change the phase of gate 1 by 45 degrees, and we can see it over here. And now we need T dagger to move it back. Let's go to IBM, and we have Hadamard gate, a T gate, 45 degrees here, and then T dagger, and returns back to the original state and phase. So today we talked about single qubits, we talked about Hadamard gate, Pauli X, Y, Z gate, and also the ST gate, how to draw them, how to get the unitary matrix, the state vector. We saw their state and phase also on the block sphere. We visualized the transition and we got the plot histogram. Then we talked about the self-inverse gates and how we can put twice to get the original state. And we finish with the gate inverse pairs, why we need S dagger and T dagger, how to create them to do the visualization, also for T dagger. So this for another video, not for today. And we also work with Quirk and we saw everything also here in the IBM platform. If you want to use the IBM Quantum Learning, it's easy. We have 10 minutes free time to work on their machines, but for now we don't need to do anything. And that's a wrap. Thank you for watching the video. If you liked it, please remember to subscribe. The button is somewhere here down below. And take care. See you on the next video. Bye.